Yeah, Dustin, do you want to kick off again?
Yes, I'm happy to.
Great.
Oh, so we saw that in essence, we saw that this condensed structure or topology on the Moravia E Theory spectrum is not essential because it is just recovered from the spectrum structure. So it's not something you really have to carry along. So you might wonder what the big deal is. And indeed, for many purposes, there is no big deals for exactly that reason. But there's one thing I'm going to get to, which is quite opaque from that perspective. And so let me give a different option for putting the same condensed structure on Moravia E Theory. So that was this, Lurie gave a new way of producing this Moravia E Theory spectrum, and he also generalized the setup. So the association works also for K, a perfect ring, and G, a formal group of pure height n. Right, like, yeah, always n over the whole spectrum. I assume you could prove the same thing using Gorse-Hopkins Miller techniques. It's all based on deformation theory, and it should always work the same for a perfect ring or a perfect field. But Lurie is the one who he did give a new approach, and in that approach he extended this setup so that you can take a perfect ring as input as well. So in particular, well, we can just take so we can just define En of S to be this Moravia E theory for continuous functions on S with values in K. That's going to be another perfect ring of characteristic P, and then the pullback of G. So G is a formal group over, implicit in this guy is our base field, perfect field K, and a formal group of height n over K. And then this is a K algebra. We can just take the induced G on that, and then take Moravia E theory in this more general way. Right, and that's explicitly describing a construction, a presheaf on extremely disconnecteds. And it's actually fairly clear from just what the homotopy groups are doing that it sends finite disjoint unions to products. Right. Yeah, I should say the pi zero of this is still just the same thing. Bit vectors on your ring, and then adjoin some extra variables. Okay. So why is this the same? Well, as before, we have a map from En considered as a discrete guy. This is on when S is a point, this is just En, right? The usual spectrum En. So we have a comparison map from the discrete thing to this new thing that I've defined in terms of the S-valued points. And you just have to check that you get an isomorphism on S-valued points, but both sides are P v1 up to Vn minus 1 complete. So can check mod P v1 up to Vn minus 1, and then both are actually discrete. And it's an isomorphism on the point. So this will be discrete because, again, you're just modding out by the formal parameters here, and you just get some version of continuous functions. So yeah. Hence it's an isomorphism. Right. So it's quite easy to see that these descriptions we're describing the same condensed structure on Moravia E theory in both cases. But you get more out of this second description. So let me go back to one of the motivating things I had, which is that the Ln localization can be built in terms of Moravia E theory and its tensor products with itself in just some finitary manner. But things get much simpler if you, so this guy was complete at P v1 up to Vn minus 1 and so on. If you complete everything at P v1, so if you complete at P v1 up to Vn minus 1, then you get what's called the Kn local sphere. And then this is really only just need one copy of En here. So when you do the completed tensor, the P v1 Vienna, completed tensor product here, it'll have En as a summand anyway. It'll have En as a retract anyway, so you only need En. So this lies in the thick subcategory generated by just this one guy, En. And in fact, you can be more precise about how to build LKNS from En. So let's take K to be FP bar and G to be, well, there's a sort of a canonical formal group of height n, but okay, any formal group of height n. And that'll be that's my K and G for building my Moravia E theory. And then there is an algebraic group, or the group scheme over FP, parametrizing automorphisms of the pair KG. So in other words, you give yourself a field automorphism, well, tensored with some parameter algebra, FP algebra R, and then an isomorphism of the pullback of G with G itself. Making the diagram commute. And actually, this is going to be a constant group scheme or a pro-constant group scheme. So this is actually the pro-constant group scheme on a group. No, I don't want to call it G, I guess. Oh, I don't know. I'll call it script G. So G is the Moravia stabilizer, so-called the extended Moravia stabilizer group. So it sits it. So since an automorphism of the pair in particular induces an automorphism of the field, and if you just asked about an automorphism of the field, the group scheme that would be represented by is the absolute Galois group, considered as a profinite group. So that's So that's this copy of Z hat here. So the constant group scheme associated to that. And then the automorphisms of and then the kernel is going to be the automorphisms of the formal group over K. So the actual K automorphisms of the formal group. And that's this really interesting fact that it's this profinite group of the units in the division algebra, units in the ring of integers of division algebra of invariant 1 over n over QP. So if you don't know what that is, never mind. It's just some profinite group that's, well, it's a p-adic Lie group, so it's essentially pro-p. There will be up to a finite group's difference. It's pro-p. All right, so non-commutative. So this one's commutative. This is Z hat, but this one is very non-commutative when at heights bigger than or equal to 2. But in any case, it's just some profinite group. And it's this nice fact that the group scheme of automorphisms of this pair is essentially constant. Okay. And then, well, so then we realize that actually this association of Moravia E theory is functorial. So we get an action of G on Moravia E theory. And well, so we have automorphisms, we have symmetries for this Moravia E theory, but we're not supposed to have symmetries of the sphere spectrum. Well, any automorphism of a ring has to fix the sphere spectrum. So there should, and then this is Kn local. So, well, we get an induced map to, if we mod out by the automorphisms or take the so-called homotopy fixed points and, oops, sorry. Yeah, I was just about to fix that. Yeah. And then this is an equivalence.
And the sphere on the left somewhere. Right?
Yeah, LKN sphere, thank you. Yeah, the only problem is, for this to be true, it needs to be the continuous homotopy fixed points. On the right. So the thing where you had to have a spectral sequence with a continuous cohomology of the group acting on the coefficient ring of Moravia E theory, converging pi star minus p of the Can local sphere. And in fact, this spectral sequence was produced, yeah? So one knows how to produce this spectral sequence, but yet people have proposed frameworks for making this action of the Moravia stabilizer group on Moravia E theory continuous, in a sense, precise. I might discuss a couple of them in a while, but the point I really want to make is that this is exactly the kind of thing that the condensed framework is supposed to do for you very nicely and easily. First of all, here it's really not enough to consider En as a discrete spectrum, because, the Moravia stabilizer group is, so we have an action of Moravia stabilizer group by taking homotopy on, say, pi naught of E. This is not continuous with respect to the discrete topology on pi naught of E and the profinite topology on G. It's only continuous if you take the adic topology for this complete local ring. So it's really kind of, if we want to formulate this, we really do have to have a world like condensed anima, where you have both a topological direction and a homotopy direction. And in this case, the topological direction is kind of adic topologies, but never mind that, it's still there. And then the homotopy direction is sort of, well, everywhere in the whole thing. So this is the kind of thing that condensed spectra are supposed to be able to do. So I figure I should show you that they do indeed do it pretty easily. But first, let's take a step back. And so what does it mean? That G acts on En. And now this here is a condensed spectrum, or ring spectrum if you want. And this here is it's a profinite group. We can also view it as a condensed group. So, right. So I'm asking just a question, what does it mean for a condensed group to act on a condensed spectrum? And it may not entirely be obvious what the answer is, but okay. If we ask the analogous question for G acting on just a condensed abelian group, or a condensed ring or something like that, then we kind of know just how to write down by hand what it means. It should be this would be a map of, you give an action map of condensed sets. And then you'd write down in diagrammatic form sort of the axioms for a group action on an abelian group, right? So there'd be some, if you do G cross, you want to say it commutes with it, I won't even try. Or on S, such that, I guess I could say just such that on S valued points, get a group action. S cross A of S. Group action on an abelian group. All right, so I guess that's the clever way to not write down the diagrams. Okay, if you're doing condensed spectra, then maybe you don't quite know how to, well, I suppose you could do the same thing now that I think about it. Some of this didn't occur to me when I was preparing it. Well, okay, you could say the same thing. So for example, you could say G maps to, you can look at the automorphisms of the condensed ring spectrum or something like that. So that'll be represented by a condensed anima, group anima. And then you could just ask for a map of group anima from G to that. But I think it pays to take a different perspective. But a different perspective is, use the slice topos. Slice infinity topos if you want over BG. So if you have any group object in a topos, you can make this BG, which Peter already talked about in his lecture. And then you can think of something mapping to BG. In fact, it is some general topos theoretic thing. This is the same thing as giving an action of G on, well, not X here, but on the pullback. So we call this the underlying object. Then it's the same thing as giving an action of G on this underlying object here. Okay. And this slice topos here, this is the same thing as sheaves of anima on extremely disconnected over BG. So you have a defining site for this slice topos. This is just general topos theoretic nonsense that if you want to specify an object here, it's the same thing as specifying a sheaf on every pair consisting of an extremely disconnected, on a category of pairs consisting of an extremely disconnected thing together with a G torsor on S. Right. Okay. So how can we produce this for Moravia E theory? Well, so let's say we have a extremely disconnected profinite set, and then a G torsor. Well, then if we apply underlines, so S, this is the constant group scheme, which is the same thing as spec of the continuous functions on S with values in K. We get a torsor for the algebraic group G over S, and so in other words, we get a map from S to B G. This is essentially just by functoriality of mapping from constant profinite sets to constant schemes with values on this constant scheme on that profinite set. But this is the same thing as the stack of formal groups isomorphic to our G over to our original G. Oh no, sorry. Yeah, this should be script G here. I knew I was going to get into a lot of trouble with this. So in particular, this classifies a new formal group. On S, which gives a new Moravia E theory. Let's call this G prime. So then we get a Moravia E theory for continuous functions on S with values in K, and then this G prime. So we're now using the extra flexibility of the second variable in the construction of Moravia E theory. When we allow ourselves to vary the height in formal group over our base ring, then we get some extra structure on Moravia E theory, and it just, when you look at what you get, you see that it's exactly an action of this Moravia stabilizer group encoded in this manner. Okay. So now, how to check that? So now we have, okay. Now we can make a precise statement, right? So this is a condensed spectrum. We just do the KN localization again in the condensed world. So it's the same thing as taking the discrete spectrum, say LNS, and then completing it at P and then up to Vn minus 1. This is also a condensed spectrum. So this is well, we had our En, our En tilde living over Bg. This was this refined construction taking into account the second variable. Then we can take global sections, or so take sections, and you get a condensed spectrum. Yeah, which you could call, so this thing has the property that when you pull it back here, you get En. And this is kind of the definition of the homotopy fixed points, in essence. It's just the right adjoint to the functor from condensed spectra to condensed spectra with G action given by taking the trivial action in essence. So that's exactly what a homotopy fixed points should be. And then, yeah, again, because any automorphism has to commute with the unit, so it has to preserve the unit, you automatically get a map like this, and you want to check that it's an equivalence of condensed spectra, which would then recover these spectral sequences that people had written down. Although maybe I should explain afterwards the connection of this story with usual continuous group cohomology, and I will. Okay. Right, so how do we check this? Well, first of all, so note that ENHG is KN local. Well, we know EN is, and then if you look at it, another way of describing this ENHG, kind of as you'd expect, is as a limit over EN, so the limit over some cosimplicial diagram. And then you have to do an internal mapping object from, let's say, anyway, if you just, taking sections over BG, you can always calculate that by resolving BG in terms of its definition. And so by general topos theoretic nonsense, the sections over this guy will be the same thing as the limit over the sections over each terms in the tower, in the hypercover that you resolve it with. And then if you see what that, and then once you pull back here, you're already constant because you live over a point. And so it turns into some diagram of this form right here. And then each of these is going to be, this is some internal Hom. This one is KN local, therefore so is any internal Hom to EN. Because the KN local category is closed, usual KN local category is closed under limits. Right, so that's just, okay, so you'd expect the KN local things to be closed under inverse limits, and I'm saying that also holds in this condensed context, and with this funny kind of limit that isn't a categorical limit, but it's sort of, yeah, I don't know. I don't exactly know what to call it, but it's limits plus internal Homs, whatever that kind of thing is. Right, so then it's enough to check mod P V1 Vn minus 1. So then we have yeah, LNS mod P V1 Vn minus 1 mapping to En mod P V1 Vn minus 1 HG. And then in fact, it's enough to check, yeah, can also tensor with with En here. So this results from the fact that for example, that the Ln local sphere is built in finitely many, can also check on, from the Ln local sphere is built in a finite, or the Kn local sphere is built in a finitary manner from En. Let's say we know that a priori. You can make a version of this argument without assuming that, but so then you're allowed to check by tensoring with En. In fact, this is basically the definition of Kn localization. Yeah, sorry. Yeah, it's already going to be complete, so I don't need to say that. And then you get En mod P all the way up to Vn minus 1, and you want to compare that to En tensor En mod P Vn minus 1. HG. And then you use the fact that this thing is just, you have to use a calculation of this tensor product, which again comes from some formal group stuff. So you have to know the tensor product of complex oriented ring spectra just corresponds to the group scheme parameterizing isomorphisms between the formal group. But in any case, that means that this turns into continuous functions from G to En mod P1 Vn minus 1 HG. And then the homotopy fixed points exactly cancel something like continuous functions from G in there. And then, so anyway, my point is that the condensed framework makes arguments like this. You reduce to the essence very quickly, yeah, using this formal stuff. So the essence of this, why this is true is that Kn local things are closed under limits, plus En tensor En parameterizes automorphisms of the universal formal group over this Lubin-Tate ring, the pi naught. And you want like that should be the only ingredients in the argument. And when you put things in this condensed framework, then yeah, your hand writes the rest, and then you just have to know those specific facts. So then we get this. So indeed, it is true in the world of condensed E-infinity ring spectra that the K-n local sphere is the homotopy fixed points for the Morava stabilizer group action on En.
Omar asked some question.
Okay, so so the K-n local category is yeah, right. So you don't want solid. You always want K-n local, which is much. I mean, yeah, yeah. So I guess it will be true that some version, yeah, you know, if you take a K-n local condensed. I guess K-n local solid solid S modules should be the same as that as a condensed category. Yeah, should be the same as the homotopy fixed points for the Morava stabilizer group acting on K-n local K-n local En modules. But I don't think you can ever take K-n local out of this and then go to more general solid things. Yeah, solid modules over the K-n local sphere are much bigger and wilder world than K-n local ones. Let me actually make some remarks related to this. So beware. Well, it depends what you mean, Scholze. I think maybe the only reasonable way to define solid LEN S modules is as En local solid S modules, because it's a non-connective ring. And yeah, but anyway, so En we just produced En as a condensed ring spectrum. It's actually solid. So for example, well, E1 is a KU P completed. But beware, if you take E1 and then take the solid smash product with E1, for example, or any En, this is not going to be P complete. So I mentioned this fact earlier that if you take P complete solid Z modules and solid tensor product them together, the result is P complete. But I had this hypothesis that they be connective in the derived world, though they only live in homological degrees. So, and this is, yeah. So if you try to do something like this in the solid world, yeah, you're gonna find that. I mean, I guess you know you're gonna still be getting the LN local sphere. I think if you do En and then En solid tensor product En and so on, you're not going to get the Kn local sphere. So this is not. This is less complete than the thing with the P completion. Yeah. So it still contains more rational information, more refined rational information than the P completion. So that's one thing you have to keep in mind in this kind of non-connective situation. Am I almost out of time? No, wait, no, I have 30 minutes. Okay. So let me make another remark. So we just talked about condensed spectra with gamma action. I'm switching to gamma now. Gamma will now be a general profinite group. What's the relation with previous approaches? So the first people to make precise this idea that the Kn local sphere is the homotopy fixed points in some sense for Morava stabilizer group action on En was Devenetz-Hopkins. So they produced a sheaf of spectra, or sheaf of E infinity ring spectra, in fact, a hypersheaf, that's quite important, on the site of finite continuous G sets, or gamma sets, such that, on the point, it's the Kan local sphere. Have the descent spectral sequence from the continuous cohomology. And okay, so that looks good. But what is the sense in which, so this is one way of encoding a continuous G action on a discrete spectrum, right? So this might look kind of funny. So what is the underlying E infinity ring spectrum here? So the stalk at the point of this site. So that's the co-limit over all open subgroups of the Moravia stabilizer group of, yeah, what's supposed to be the homotopy fixed points, which is just something that they posit as part of their construction, is something whose Kan localization is Lkan. Oh, sorry, it's En. So it's some other kind of decompletion of En. So so they get around this problem of the action of gamma not being continuous for En as a discrete spectrum by saying, okay, there's a decompleted version of En, such that when you can localize it, you get En, and there the Moravia stabilizer group with its profinite topology does act continuously in a sense. And they build it just by producing this kind of object here. And then other people had other approaches, but I don't understand them so well. So I'll stick to what explaining the relation with what Devnitz-Hopkins did. So here's so then let's step back a second and we can ask, what is the relationship with between the two ways of encoding a G action, or a gamma action? So let's say that X is a discrete spectrum, or a discrete anima even. So two ways of saying gamma X on X. Well, so one would be view X as condensed, and take what we discussed. And the second thing would be promote X, find a sheaf on finite continuous gamma sets with stock X. So these are two reasonable ways to encode a notion of a continuous action of a profinite group on an anima. And there's a strong relationship between them. So the claim is that the infinity category of discrete condensed spectra, or anima, with continuous action, of profinite group gamma, is the same as the Postnikov completion of the infinity category of sheaves of spectra, of anima, on the site of finite gamma sets. And the way you see this is by seeing that both of these are the inverse limit over sheaves on a point mapping to sheaves on gamma, sheaves on gamma cross gamma, And these are usual sheaves of anima on usual topological space. Right. What is this Postnikov completion? So let me explain it this way. If I were to not ask about a discrete condensed anima with an action of gamma, but n truncated discrete condensed anima. So if I only want homotopy information to go up to level n and then stop, then I would get the exact same thing. I wouldn't need to say Postnikov complete. I would just get this, and there would be sheaves of n truncated anima here. So on the level of truncated things, they're all the same. But in case of this option here, this condensed option and this inverse limit option, which are equivalent, the infinity category of the infinity category of not necessarily truncated guys is the limit of the truncated options. So giving a condensed spectrum with an action of a profinite group, a discrete condensed spectrum with an action of a profinite group is the same thing as compatibly giving a continuous action on each of its Postnikov truncations. On the other hand, in this middle option here, the sheaves on the usual site of finite gamma sets, it's very much not the case that a sheaf of anima is giving a sheaf of anima is the same as giving its a sheaf of n truncated anima in a compatible way. Yeah, so you'd have to just formally replace this thing by its Postnikov completion. And I'll just make a remark that if the virtual cohomological dimension of gamma is less than infinity, which holds if gamma is, say, a Moravia stabilizer group, then Postnikov completion is the same thing as looking at hypersheaves. So then it is just again a full subcategory of this option with sheaves. So right. Yeah, so then if you want to recover the yeah, so then using these equivalences, you can recover the Devenitz-Hopkins approach to this continuous action from the condensed one and vice versa. So you could take, so for example, yeah, you could take.
Well, except that they don't have an action on something discrete.
What's that? No, yeah, you have
They
to
don't
build.
have
Who doesn't? What?
Devenitz-Hopkins, they don't have an action on something discrete.
No, they do. They do on this decompletion of Moravia E theory.
Okay, but we don't. Or
no, but we
not
can build it. So let me say how you can recover one from the other. So if you want to get Devenitz-Hopkins from this one, you can make a site of on finite G sets by taking the homotopy fixed points in the condensed set for any open subgroup, and then that will, for formal reasons, be a sheaf, and then it will actually be the Devenitz-Hopkins sheaf. Yeah. And so it is encoding a gamma action on a discrete condensed spectrum, a bit of a funny one, which is artificial. Doesn't really have any significance as far as I know, except that it's what pops out, but you do get that. And if you want to go the other way around, then, oh wait, can you go the other way around? You take, yeah, you take the Devenitz-Hopkins thing, which is a discrete condensed anima with an action of gamma, and then you complete it again at p v1 up to vn minus 1. Now, in this world of condensed spectra with a continuous action of their Moravia stabilizer group, and then you'll produce, you'll produce the thing we talked about. But the construction that we gave here is kind of much, I would say, a lot easier than what Devenitz-Hopkins did. They had to by hand build each of these things and verify all these properties and so on. Whereas, it comes quite naturally in this condensed framework. Okay, I think that's all I wanted to say about Moravia E theory. Oh wait, no, there's one more remark I want to make. Yeah. Since I just explained that the two approaches are essentially equivalent, or it's very easy to pass back and forth between them. Therefore, you might think, okay, why do we care about the new approach? And indeed, for most purposes, you don't have to care. The Devnitz-Hopkins approach is perfectly usable for everything I've had to do so far, at least. I haven't needed to use this condensed thing. But there's one setting where the condensed way approach is, I think, the only reasonable one. And that's if you're talking about transchromatic homotopy theory, so-called transchromatic. So what is that about? So we just said that the Kn local sphere is the same thing as the fixed points for the Morava stabilizer group. And the Kn local sphere and the Kn-1 local sphere and so on, all the way down to the K0 local sphere, these kind of build up and all contribute to form the Ln local sphere, which is this tower, which participates in this tower, which limits to the sphere spectrum. But if you want to know how they build up, then you're asking about interactions between height n phenomena and height n-1 phenomena. And that's kind of a very subtle thing, and it's characteristic of that's what transchromatic homotopy theory is about. So there you study things like LKn-1 of Morava En, or even LKn-2, or you even have to get into things like this. Now, what do these look like on the level of coefficient rings? So if we take pi0 of LKn-1 of En, so what do we have? We have En, which is Witt vectors on K, and then we complete with respect to U1 up to UN-1. And then we're supposed to take the Kn-1 localization of that. So that's going to be only required to be complete with respect to up to the UN-2. But then whenever you mod out by UN-2, UN-1 is supposed to be invertible. So this gets replaced by inverse limit of, well, let me write it, Witt vectors K, how to write it, U1, UN-1, and then invert UN-1, and then you recomplete that at the previous variables, P, U1, UN-1. And in general, if you're interested in fully understanding transchromatic behavior, you're going to be alternating, inverting, and recompleting several times. And this is something which is not a topological ring. And it's a complete mess to study classically. So unlike in the situation of the coefficient ring of Moravia E theory itself, where you can just work with it as a discrete thing and the topology is recovered from the algebraic structure just because of, say, this maximum completing, you can complete out the unique maximal ideal and you're okay. Here, the topological or condensed structure is not at all determined by the underlying discrete ring. You really have to carry it around as part of the structure. And in classical terms, it's even difficult to say what this thing is, like what exact structure you're talking about. But in the condensed framework, it just is what it is. There's nothing to be said. You take this condensed thing, you take a co-limit of copies of it along this, inverting this thing, and then you recomplete, and okay. And we've done some investigations of the algebraic analog of this, and so far we haven't seen it behave in any pathological ways when we plug it into our framework. So I think if you're a chromatic stable homotopy theorist and you're interested in using this condensed stuff, this is. I mean, this stuff is not easy, this transchromatic stuff, but that's where it could really pay to use this new framework that we're discussing. Okay. Any questions?
Hey, Dustin.
Yeah.
So this Morava stabilizer group is not quite constant as a group scheme, right?
Well, I passed to the algebraic closure, right? So.
Oh, okay.
Yeah, it is. So I made this extended Morava stabilizer group. So the action of the Galois group on the units in the division algebra is accounting for the non-algebraicity over over the finite field, for example. Yeah, it's just another way of, yeah. I think I got it right. I mean, it's been a while since I've actually.
No, I was just wondering if you, if there's also an automatic way to build that into the setup.
Yeah, I mean, I think it is encoded in this extension of profinite groups, but yeah. I hope I didn't mess something up in that description, but yeah. Yeah, oh yeah, oh Shafar, are you saying that the action is not really it's only an action by inner automorphisms? It's not really an honest action on the group? Yeah, I don't know. Yeah, something like that, I don't know, yeah. Okay, so there are two questions coming through in the chat. What about the algebraic K-theory of Moravia E theory? Yeah, what about it? Hard to calculate, right? I mean, you want to use TC, I guess, and then, yeah, you use some localization sequence to reduce to connective Moravia K-theory, then you use TC. I don't know any other approach, but then I guess it's hard to make the calculations. You probably know more than me about that. Oh, the profinite descent. Oh yeah. Yeah. Yeah, I'm trying. I'm not too confident. I mean, so yeah, I guess me and Akil Matthew and Justin Noel and Nico Naumann, we just proved some finite descent result in this Devonitz-Hopkins tower for Kn+1 local K theory of there, at least for P groups. But we don't know how to get hyperdescent yet. I'm trying to come up with good ideas, and I'm hoping that some of this, well, actually some stuff that we're not going to be explaining here, but yeah, I'm not giving up yet, but I'm also not completely confident that I'll be able to say anything about hyperdescent. I'm also kind of hoping Akil will come up with another great idea to get everything going. Right? How special is this story about the condensification of the action of Moravia stabilizer? What did we use about EN? We used a lot about EN. I mean, we used the very nature of the construction of EN, that it takes an arbitrary formal group of height n as input. Any guess on what KEN solidified is? Yeah, there's a very reasonable guess. So I mean, I think one, yeah, it should even be within the realm of being provable. So again, you can look at this localization sequence. Oh, I'll draw it in a very non-standard way. And then, so this is, I guess, Blumberg-Mandel maybe? Or they didn't do the general case, right? Who did the general case? Was it Barwick and Lawson? Yeah, yeah. K-theory of the coefficient ring. And this should also work as condensed spectra. And then the solidification of this should be the same thing as, well, the solidification of this should be the same thing as the inverse limit of the K-theory of the quotients, right? So you can pass the inverse limit through the solidification there. Basically, the rule of thumb is, well, sorry, we should take K to be a finite field. So the rule of thumb is if your ring is locally compact, then you can do then the solidification of the K theory will behave nicely, and you can do this kind of thing. So I should probably take K to be a finite field. And then the same thing will work here. So you can make a tower of E infinity of P V1 Vn-1 torsion E infinity rings, which limits to this. And then that will be the inverse limit of the some K theory this tower. You can build some kind of Adams tower, for example. And then, yeah, then you get this as the cofiber term. So it should be what you expect, some version of continuous K theory. Doesn't mean you can calculate it, but at least in principle, you can reduce it to K theory of discrete rings. There are more questions coming in. Here's Tomar. let's say I have a stable compactly generated symmetric non-compact unit. Peter, did you manage to parse this question?
Maybe.
I actually have a microphone now, so I think I can use my voice.
Oh, Tom,
Hi.
hello. How are you?
Hi, good. It's all amazing stuff, by the way. I'm really enjoying it.
Oh, I'm glad to.
Let me try to ask my question. So I was wondering, you know, the K and local category doesn't have a compact unit,
Right.
and it seems to me that in such a situation, you could probably get this kind of condensed structure by presenting your unit as a co-limit, and then kind of homing from the unit, take as a discrete and take the limit. And
yes, you can. That's exactly right. Yeah. Yep. Mm-hmm.
Okay, so that's what I was asking, kind of lengthening.
Let's give a little model of this for the people following along at home. So, so Z, yeah, in the p-complete category, I guess you even see this phenomenon there, right? Like in p-complete abelian groups, or in the derived context, say the unit is not compact, but only things like z mod p to the n are compact. But you can write this as the co-limit of sigma inverse z mod p to the n. Well, you might think the co-limit of this is sigma inverse of qp mod zp, but when you p-complete that, you get exactly zp in degree 0. And then, yeah, so now if you take any derived abelian group M, then mapped from this co-limit is exactly going to be presenting inverse limit of M mod P to the N. So now if you do this in the condensed context, this inverse limit is, yeah, automatically putting in the inverse limit topology, so to speak, and you're doing exactly this P completion. So yes.
Thanks.
Sure.
There doesn't seem to be more questions.
Right. I think I'll stop early instead of trying to cram something into, 10 minutes or whatever. So I'll give everyone a break. So see you guys tomorrow. It's me in the morning tomorrow. So yeah, be careful.
Oh wait, but before you go, while you still have it on the screen, what was sigma inverse here? T-looping?
Desuspension. So shift by -1 in triangular
desuspension.
category terminology.
Okay,
Yeah.
thanks.
Mm-hmm.